so let's talk about the effect of lone pairs. So lone pairs are going to end up occupying more space. So they're going to occupy more space on the central atom than bonding electrons. The reason they do that is because their electron density, it's not going to be shared between two bonding electrons. Instead, that electron density is exclusively on one atom. Specifically, we're going to be talking about the central atom, because remember, we look at the central atom when we talk about shapes. So let's talk about this repulsion, okay? So you can have lone pairs and you can have bonds. The biggest repulsion I have to deal with is if two lone pairs are next to each other. So lone pair to another lone pair is going to be a really high repulsion. Two lone pairs really don't want to be next to each other. So that's the thing that I have to worry about the most, is that lone pairs do not want to be next to each other, right? Next is if it was a lone pair next to a bonding pair. So think about a lone pair next to a bond. It's not happy in this case, but it's happier than if it were next to another lone pair. So this lone pair is okay with being next to the bonding pair because it'd rather that than a lone pair. But the best thing would be if it were just a bonding pair next to a bonding pair. That's my lowest. They're all going to repel because they're all electrons. But that one doesn't repel as much. Okay? So what happens is if I have lone pairs on my central atom, it's going to distort those bond angles. It's going to push things away from it. So when it pushes things away from it, it says get away, and so it's going to make those bond angles end up being smaller. Okay? So my bond angles, all the ones that I just learned from my parent geometries, those electron geometries, these are all going to be smaller than the expected. All right, so let's look at this. So here's a bonding pair. You see how much space? My electron density is kind of taken up between the two nuclei. They're shared between, okay? So it doesn't take up, it takes up space, but not as much. Here, look at my lone pair space. Look, it goes kind of like all the way out here for if it's a lone pair on one atom. So lone pairs take up a lot more space than their bonding pair counterparts. Okay, so what's that going to do to our shapes? So now we have to learn some sub-shapes, some derivative shapes. So that's why we learned the parent shapes, the perfect shapes, and then we're going to distort them. Okay, so the molecule shape is going to be one of those basic ones that we just talked about. If all the electron groups are bonds. So if I have nothing but bonds, it's one of my nice, pretty geometries we just talked about, those electron group geometries. And all the bonds would be equivalent. Okay? But if I have lone pairs, okay, then what happens is now I'm going to have distorted bond angles, different bond lengths. So now I'm going to have a derivative shape. So we're going to talk about those parent shapes and then talk about, well, how are they going to differ? How are they going to change? All right, so now we're going to start talking about those molecular geometries, those subgroups on the next lecture.